Swayam Prabha. Digital India. Educated India.
100 versus 101, right? So if I was part of A, I would have repeated 101 times, in which case it gets the status of being the majority. If I was not in A, it would appear still 100 times, but 100 is a hung parliament, okay? 100 is still not a majority in a stream of length 200. Is that clear? Okay. By the way, till when is the first session? Is it till 11? Okay, I have half an hour, okay. Are you clear with this approach? There is one bottleneck, that which is the fact that Bob doesn't even know the cardinality of A.
We have a universal set U, and Alice would say the number of bits like N, which is there in the
No, what Alice sends is also up to you. So in this algorithm that we are proposing, Alice is just going to put the numbers in the stream. By the way, the stream needn't be binary, because when you are thinking about a streaming algorithm, the contents of the stream could be integers, it could be edges of a graph, whatever, right? But when you are looking at the storage space, you are going to store things in binary. So whatever this guy walking around the stream with the notebook in hand will be noting down will be binary. But the stream could have cats and bats. Okay. So is this, what is your name, by the way? Debashish. So is Debashish's algorithm clear? Suppose you know the cardinality of A. Okay. So the mental block to many, I am assuming, would have been that majority versus non-majority can be just distinguished by one bit, one occurrence. Okay. Like earlier in Amy's algorithm, we could distinguish between one occurrence and two occurrences. This is between some 100 occurrences and 101 occurrences. Okay. Now the next smart move. Bob doesn't know the size of A. Can you still do something? Actually, this is simpler.
maybe the Bob stream is of some particular cardinality, we might say. We can break that Alice's stream to that particular cardinality. That could be substreams, and we can.
So Alice then should know the length of Bob's stream, is it?
No. The Alice has sent a stream, right? So suppose let us say that Bob's stream is of cardinality K, and Alice's stream is of
I get you.
2K. Then Bob will break that 2K stream into K and K.
And then do a separate check, because at some point it will be a majority. Yeah, it would have worked, but unfortunately Alice is not sending the entire stream to Bob. Alice is only sending whatever that very small storage, the algorithm is only, Alice is only sending the memory footprint of the algorithm, the space used by the algorithm, right, the notebook, not the entire stream, right? So we are assuming, we have this majority detection algorithm is a very efficient algorithm, its storage may be very small and so on. Unfortunately, it is not, but that's what we are assuming. Okay. Any other suggestion on how to come out of this, cardinality? It's a borderline issue. I mean, it's not a great thing. You would all have heard of padding, right? Can Alice ensure that her stream is always of some length, irrespective of the size of A? Right? Can Alice ensure that her stream will always be of the same length, irrespective of what is A?
So she can take the n numbers. She can, even though her set is, if it is a proper subset of the original universe, she can take the size. We can have a size of the universe as such as a whole. Pad it with some other number.
Exactly. That is the key. You pad it with some other number. Pick a number which is not in your universe. For example, 0. Okay. This universe, okay, we don't have it in this slide. The universe was 1 to n. So pick 0 or some, n plus 1 or something. And Alice would put in all her contents, the elements of A, and then just fill the remaining entries with zeros. Okay, how many zeros? Size of universe minus size of A. Now Bob's one worry is over. He already knows the length of the stream, it's going to be n. So how many copies of I will he place in the stream? N copies of I. So if I was in A, I would be repeated n plus 1 times, which is more than half of 2n. So it is a majority element. And if not, I will be repeated only n times, it's not a majority algorithm. So based on the answer that the majority algorithm gives, Bob will know whether I is a member of A or not. Are you with me? Okay. So yeah, so this is what I just said. Okay, make sure that everything clear? Oh. So now so far the story was looking like it's a comedy, right? It's our chance to help Alice and Bob. Okay, but I was lying. Okay, it's actually it's a dark story. Okay, our idea is really not to help Alice and Bob. Our idea is to show that majority detection is hard. Majority detection is difficult, that it needs at least so much of storage. Okay, so we are going to kind of invert the game. We are going to make the same setup where one algorithm helps another algorithm, but we are not going to use it to really help the other task, but we are going to say that the first task is hard. Okay, that's the idea. Some of you would have already known it, but if you are seeing it for the first time, it may be a bit of a confusing thing. Okay, so these things are called reductions. What we did, you take one problem, reduce it to another. Those are called reductions. The reductions have a bright side, which is like you feel as if you are solving one problem using another problem. But reductions also have a dark side, where you say that one problem is difficult because another problem is difficult, and the critical thing is that the direction of reduction. You should be very careful based on what you are going to do, which problem you are going to reduce to which other problem. Okay. By the way, this is the most important slide in the presentation. Okay. This reductions is not just limited to streaming algorithms or communication complexity or anything. It was all the way there from Turing machines. You first show that the halting problem is impossible for a computer to solve, and then you show that many other problems are impossible, because if you solve that problem, then halting problem can be solved, and so on, right? So this reductions has a history starting with Turing Church, that time itself, complexity reductions, right? So that is why I say that this slide has its value even outside of this talk. Okay, so let's go through it slowly. First, let's think about the bright side. Okay, you want to solve problem 1, but you know how to solve problem 2 using some R rupees. Okay, that's what you know. You want to solve problem 1, you know already how to solve problem 2. So this is natural, right? You try to reduce problem 1 to problem 2. Maybe in this reduction you pay some cost, some little R rupees, but now you can solve your problem 1, using capital R plus small r amount of money. Straightforward, right? This is like, for example, you know how to sort and you want to find the median, or let's say you want to find the maximum. You can always do that, right? You do the sorting and you can reduce finding the maximum to taking the last entry in a sorted array. Okay, so you know to solve one problem, you can use it to solve any other problem which can be reduced to it. This is easier to think, it is easier to get your head around, and it also gives a bound on, an upper bound on the amount of resources you need to solve problem 1, right? The reduction costs you some little r, solving problem 2 costs you capital R, so solving problem 1 together costs you little r plus capital R, right? Usually this little r is very small, we ignore it. It's almost with the same cost as solving problem 1, you can solve this. Okay, this is not necessarily optimal. For example, maximum you can solve in linear time. Reducing it to sorting is not a good way to do it. It will take you actually order of n log n time, but it still gives an upper bound. That's what This is the bright side of reduction. Is this clear? It's a simple concept. Okay. The dark side of reduction is what we need. Okay. Here again, you want to solve problem 1. That much remains the same. But unfortunately, what you have in hand is not a solution to problem, some other problem, problem 2. What you have is a lower bound to problem 2. What do I mean by that? You know that solving this other problem, problem 2, requires at least bigger amount of money. Okay, you do not know how to solve problem 2. You know that problem 2 is an expensive chap. It requires at least bigger amount of money to solve it, right? Now the third bullet point, in fact I have intentionally wrote it and striked it out. The reduction this time has to be in the opposite direction. Okay, you are not reducing your problem, your favorite problem to problem 2. No, for the dark side, you are reducing this known difficult problem to your problem. This is how all the hardness reductions work, right? You reduce halting problem to your problem to show that your problem is hard. Okay, this is a very common mistake. That's why I know I'm kind of boring you to death by repeating it so many number of times, but even after repeating it n number of times, people get this hardness reduction, the direction wrong. So please be watchful about that. So you know how to reduce problem 2, the hard difficult problem, to problem 1 using again little r amount of money. Now what can you say about problem 1? Nothing positive, nothing optimistic. You can say something very negative, something very pessimistic about problem 1. That problem 1 would require at least big R minus little r of resources, right? This is now the argument is by contradiction. You know, suppose not. Suppose you did not require capital R minus small r amount of money to solve problem 1. If you could do it with smaller amount, it will violate the second bullet point, right? How? Because I will reduce problem 2 to my problem 1, I have only paid little r amount of money. Now suppose problem 1 could be solved with fewer amount of money than capital R minus little r, then my total expenditure is something smaller than capital R, right? Because capital R, something smaller than capital R minus small r plus small r. Are you with me? Okay. So this is a proof by contradiction. If you, black on black won't work. Okay. So if you can't do this, then this will contradict the second bullet point. Okay. If you, when I say contradict the fourth bullet point, it means if you can do it with smaller amount of money, it's an indirect way to solve problem 2 also with a smaller amount of money. But we have the gold standard. We assume we have a proof that you don't have any way to solve problem 2 with fewer amount of money. Okay. In the halting problem kind of case, the gold standard is really a theorem. But in the complexity case, when you talk about NP hardness, the gold standard rests on a conjecture. You know, people believe that the SAT cannot be solved in polynomial time, and hence if you can reduce SAT to your problem, then your problem also cannot be solved in polynomial time. Okay. The key part is that you have to reduce SAT to your problem, not your problem to SAT. Is this clear? Okay. As I told you, take it down slowly. This is the slide that will be useful even outside this context. By the way, this R would stand for any kind of resources. It could be time, it could be space, right? I have kept it general in this slide. Okay. So now time to patch everything up. Okay. So yeah, the first half of the slide you have already seen. Now let's try to do a reduction. Okay. By the way, if you go back from in this setting of where you tried to help Alice and Bob solve the index game using the majority detection algorithm, in this dark side of reduction kind of argument, what you end up showing is that there is no streaming algorithm which can have a storage less than n. Why? Okay, think about it. I am going to claim that requires at least n bits. Using this, the dark side of reduction argument. Okay, how would the argument go? Suppose there was a streaming algorithm which had a storage which was less than n. Okay, this is how any proof by contradiction will start, right? You're familiar with the proof by contradiction argument, okay? But somehow I still get fascinated when I talk about it, right? In the analogy of chess game, right? This is like a gambit, and many textbooks call it there is this queen gambit if you know chess, right? You sacrifice your queen, but you still, win the game. But proof by contradiction is almost like a king gambit. You start by assuming what you are trying to prove is wrong, reach a contradiction, and thereby you argue that hence the assumption was wrong. Okay, so here suppose the assumption is the following. Suppose you could solve the majority detection in a streaming setting using fewer than capital N bits, then Alice and Bob could solve the membership problem by communicating fewer than n bits, right? Because when you are running this, two-patch kind of streaming algorithm where Alice has her stream with her data plus 0 padding to make the length correct and so on, the streaming algorithm runs through this. This is this supposed streaming algorithm which uses fewer than n bits, right? When it reaches the end of Alice's part of the stream, the storage, because anyway the maximum storage is fewer than n bits, the current storage will also be fewer than n bits. That is what is communicated across the channel. Bob will pad n copies of I, continue the run of the streaming algorithm, kickstarting it using this stealed storage, and at the end of the day you will know whether there was a majority element. Thereby Bob knows whether I was a member of A or not. But what is the big deal? Why did you make it all complicated? The total communication was now fewer than n bits, because the memory footprint of the supposed algorithm was fewer than n bits, okay? And we just showed 2 slides ago that this is impossible. Index game really requires n bits. Hence, there is no supposed streaming algorithm which can store fewer than n bits and detect majority. Okay, this is the idea. Yeah. Okay, so now let's come back to our, in the last 15 minutes we will do the last reduction that I want to do. Here our aim is to not help Alice and Bob, but to show that graph connectedness requires a good amount of storage. By the way, maybe I should have remarked one thing. When I said this majority requires at least n bits, in class, in Arijit's lectures, you would have seen probably, better algorithms, but they were approximate algorithms, okay? The lower bound that I just told only works for exact deterministic algorithms, okay? If you are ready to only estimate whether something is a majority or not, or have it with some probability of success, you need a different version of this communication game. There are communication games where also the task is to, in some sense, Bob only wants to know some approximate information about Alice's set, or Bob is ready to tolerate some amount of randomness in deciding that he is ready to tolerate a probability of error. Everything is in the same setting, just that the starting communication game problem will also be of that flavor. Okay, so coming back, graph connectedness. Okay, so remember what was the problem? You have an n vertex graph. This vertex set is known to everybody. Edge set is coming in a stream, and you have only one pass through the stream, and you want to check if whether this graph is connected. Okay, the obvious algorithm was to run Kruskal in a stream, which essentially maintains a spanning forest. So using since it's a forest, you will need to store only n-1 edges at the maximum, and each edge essentially means you store the 2 endpoints. But since the vertices are from an n element universe, storing one vertex means storing log n bits. Right? The one vertex is an element of a n element universe. So one vertex requires log n bits, one edge requires, therefore, in the naive way of seeing it, it requires 2 log n bits. Okay, so n-1 edges will require n-1 times 2 log n. It's roughly twice n log n many bits. That was the algorithm. It is known that you cannot do smaller than n log n, but that proof, That proof will take one full class. Okay, it's not that complicated. It's a 2016 paper. It will take one full class, but we are not planning to do that. We will instead show a weaker lower bound. We will show that at least n bits is required. So there is a gap between what is the best known. We are not going to reach all the way. Okay, so our task is to show that any streaming algorithm for connectedness needs to store at least n bits, where n is the number of vertices in the graph. That's a task. Clear? We need to show that any graph streaming algorithm, not the Kruskal online, okay, any supposed connectivity testing algorithm on the stream will need a storage of n bits, and that's our problem 1. Now problem 2 is not something which we know how to solve problem 2, but that's not what we care about. About problem 2, what we care about is that it requires at least n bits of communication. It is a set disjointness problem, the second communication game problem that we had talked about. Alice has a set A, Bob has a set B. Bob wants to know if A intersection B is empty or not. Okay, we saw that it requires at least n bits of communication. Okay, yeah. Now it's your turn. Okay, can you try to construct? Okay, here, okay, we have lost. How do you construct this string? Okay, maybe we will do it. Is the task clear? It's a complicated task, so make sure that you understand what we are about to do. Okay, we want to reduce this disjointness game. Okay, somehow we have to show our problem 2. The disjointness game, for which we know a lower bound, can be reduced to the graph connectivity game. Okay, so we should take this disjointness game, then make Alice construct one part of the stream, then make Bob construct the remaining part of the stream. But unfortunately, now this stream is going to be stream of edges, not stream of numbers, right? Yeah. So I think. So let's, as a hint, this is the soul of this reduction. Okay. So you are given two subsets A and B of an universe U, as is in the setting of the communication game. A is the set with Alice, B is the set with Bob. But forget about Alice and Bob for a moment. Think that you have two subsets A and B of the same universe U. Okay. And I want you to imagine a graph construction. Okay. Some procedure to construct a graph such that if A and B are disjoint, then it results in a connected graph. If A and B are not disjoint, then it results in a disconnected graph. Or the other way around. Since it's a binary decision problem, it's okay. I just want to distinguish A and B being disjoint or not using the property that the resulting graph is connected or not. So it's okay if connectedness maps to disjointness or connectedness maps to non-disjointness. Okay, you are allowed to flip. But what is the first thing that comes to your mind? This is the toughest question I am going to ask in this lecture, and anyway the lecture is ending in 5 minutes. Okay, so you have a universe U, you have two sets, say A and B, and there should be some procedure. The procedure should be common. I am going to draw two cases, but the procedure should be common in both cases, whether A and B are disjoint or not. You should have some way of saying a graph construction, so that in this case the graph that you connected, let us say is, okay, let me say in this case the graph that you connected is construct is disjoint, whereas in this case the graph that you construct is connected. Bingo, very good. Okay, so let's try to that. Okay, try doing that. So, oh, I did not ask your name. What was your name? Shivani. So what Shivani is suggesting is, think of this universe, which was numbers 1 to 1 million or so far, as just vertices of a graph. That's the first idea. Okay, these numbers 1 to 1 million, 1 to n are just vertices of a graph. Okay, so and for any two vertices which are in A, you put an edge between them. Okay, so this whole of A will start looking like what? What is this kind of graphs called? It will look like a complete graph or a clique, right? Similarly, she also said put an edge between all the vertices in B. So B will look like another complete graph. But if A and B are disjoint, then the final graph that you get will be a disjoint union of two complete graphs, which is disconnected. Whereas if they were like this, right? If there was even a single vertex in common, that vertex is connected to both sides. Okay, so you get a connected graph. And this reduction is very useful because Alice has to construct her part of the stream, but she knows what A is, so she can construct this region. I should have actually used two colors maybe. So Alice can easily construct this part of the graph. In either case, Alice doesn't have to know whether A and B are disjoint, which she doesn't know. She just have to pick every vertex in A and every pair of vertices in A and put an edge between them, right? Similarly, Bob can construct this part of the graph without really knowing what is A, okay, in either this case. Is this clear? Is this completely clear what Shivani's suggestion is? So we have reduced disjointness problem to connectivity problem, but this has two bugs. Okay, good. In fact, I am very thankful that Shivani came up with this. That's why I had called this as attempt 1. So okay, before going to attempt 2, anybody spotted the bug here? Okay, one bug is in some sense a borderline thing. Okay, now suppose A was empty. Okay, I know it sounds very kind of but I mean when we design algorithms we even have to treat this borderline case, right? Suppose A was empty, empty set is disjoint with any other set, right? Whatever is B, A is disjoint with B. So we wanted a disconnected graph, but we only had this one click on the B side. That's one problem. Is there any quick fix for that? Either you restrict the problem to non-empty sets, good, okay, or just have two additional vertices, okay, which is not in U, like our padding example, just have two more vertices, one which you will always put in A, include with A, and one which you will always include with B. So these edges you will also add, right? So you will never have a problem of an empty graph, right? So your vertex set of the graph that you construct will have U union, okay, my U and union is looking the same, okay, U union some S and T, where this is S and this is T, same thing here, okay. So the problem was that A was empty, just either assume it is not so or you put that, okay. This is the small issue. And the bigger issue is that even when A and B were empty, this had a serious bug, okay. Suppose we never said that A and B covered U. There are potentially, vertices which are neither in A, nor in B. What happens to them in G, in the graph that you construct? You do not, neither Alice adds any edge between or from a vertex outside of A to anywhere else, neither does Bob. So these guys kind of remain isolated vertices in both cases, even when A and B overlap or non-overlap. If there is a vertex which is neither in A nor in B, then these remain as isolated vertices. This is the big problem. Once you have an isolated vertex, by definition the graph is disconnected, right? The connectivity algorithm is not something you can tweak. We are going to, our attempt is to have a lower bound argument which works for any connectivity algorithm in the string. So in this case, if A and B happen to be empty, that we have fixed, but if A and B happen to be not covering U, you will end up having isolated vertices in the resulting graph G that you construct. Is the issue clear to everybody? Is the issue with Shivani's suggestion clear to everybody? Okay. Now you really need a smart idea to much more. This kind of a graph construction is something that you will get if you are in graph theory. Okay, connectivity, components, right, vertices being thought of as numbers. If you do like 1 year of graph theory, you would probably see this in. But now that you have run into a problem, how do we fix it? It requires a tricky idea, but not very complicated. I'm sure some of you would be able to come up with that. Okay, we're running out of time. Okay, so I mean, I really wanted to wait more. In fact, I had left space for, attempt 2, attempt 3, but I think I'm kind of running out of time. Okay, so what we do is something very strange. Okay, so you have this, bad color. Okay, Alice's color was red, right? Yeah, so Alice has this set A, right? And this is her universe. This is the common universe for everybody. Maybe universe I should draw in black. This is the common universe for everybody. Alice takes this extra vertex S to be safe, just to make sure that A being empty doesn't hurt you. This extra vertex S to be safe, and does the opposite. It used to connect S. In fact, by the way, you would have noticed that even in this 2 slides ago, you really needn't put an edge between every pair of vertices in A. You can make this S as a universal vertex, this S as a universal vertex, and just connect everything to S. For connectivity, you don't need the whole clique. It would be like, a star graph kind of thing. One common vertex connected to everybody. Similarly, B will take T and connect everything in B to T. Okay, that was enough. In fact, you will get a sparser graph. Your stream will be smaller. You will be done with it earlier. Otherwise, you will have n choose 2 edges kind of in the stream. Now you will only need. Okay, that's a simple modification. What I'm going to say now is to invert this. Alice is not going to put an edge from S to A. She anyway cannot put an edge from S to B because she doesn't know B, but she knows A complement. Okay, because she knows A, she knows the universe. So she knows what is U minus A. So Alice will put an edge to everything that is not in A. Okay, so this is A, S to A complement. Okay, now what will Bob do? Let's say Bob has, in this case I have drawn the overlapping version, that is his set B, and Bob will again take his extra vertex T. If B was non-empty, he could have taken something from B. Okay, but since I don't want to keep distinguishing these 2 cases, I'll take T to be some new vertex not in the graph. And what will I connect to? B complement. Okay, there you don't know A, so it cannot be. So it will get connected to everything in B complement, and there is one magic edge that you add. Okay, maybe I'll put it in some another color. I mean, not much of a magic. Okay, that connects S and T. This is the construction. Okay, is this graph connected or disconnected? Wrong. Yeah, but that's not a necessary condition for connectivity. You only need a path, but there is another reason why it is not connected. Yeah. That's okay. The vertex set of the graph that we are going to construct is U union S and T. Okay, I intentionally tricked you while drawing the picture. This graph is not connected. Can you see? There are vertices here, right? In this A intersection B. Are they connected to anywhere? No, they are not connected to S because S only connects to A complement. They are not connected to T because T only connects to B complement. This is both in A and both in B, hence it is not in A complement and it is not in B complement. Strikes? Okay. Whereas, if they were disjoint, in case 2, if A and B were disjoint, there are other vertices here, I don't care, right? What happens to S will connect to all these guys and these guys. Bob's T will connect to these guys, and this extra one edge will connect S and T, because if A and B are disjoint, then A complement and B complement together covers the universe. Okay. So, in fact, somehow we have mapped disjointness to whether they cover the universe or not. If A and B are disjoint, then A complement union B complement. Okay. If A intersection B is empty, then A complement union B complement is equal to the universe, right? It's just De Morgan's law. If you, but don't think of De Morgan's law. Think about the picture. Okay. Otherwise, after you write it down, you see that it is De Morgan's law. Okay. Is that clear? Whereas, if A, in fact, this is an if and only if, right? If A intersection B was non-empty, then the poor guys who thought they were really lucky, they are liked by Alice, they are liked by Bob, but at the end of the day, Alice kind of, completely inverted her thing. She did not connect to anybody in her favorite list, but only to those outside of her favorite list. So is what Bob did. So these guys who were in both Alice's and Bob's favorite list are now isolated. Okay, so that's the graph construction. Okay, so this is the summary of what we did. Okay, my earlier drawing would have been clumsy, so try to see if you can make this out. Okay, the blue is Alice's set, the green is Bob's set, and this is how the graph is constructed, and this is how it looks like under these two cases. Okay, the slide has more. This part as of now, I want you to be clear about what is above this. Okay, so you are given these two sets A and B, which are known to be, you are also given U, you are known that A and B are subsets of U. How do you construct your graph? The vertex set of the graph is U together with these two extra special vertices, nothing big about them, just to make sure that you will still be good when A is empty and B is empty. That's the only role of these two extra vertices. And what are the edges? S to everything not in A. Okay, it is U minus A. S to everything not in A, T to everything not in B, and ST. This is the graph, and what you should remember about this graph is whether this graph is connected or not will depend on whether A and B are disjoint or not. Okay, maybe the other way, I don't care. Okay, vice versa. How is the stream going to be constructed? Alice can put all the SX edges, right? Why? Because she knows what is A, so she knows what is A complement. So she, in her part of the first part of the stream, she will include all these edges. Okay. In Bob's stream, since Bob knows B, he knows B complement, he will include all the edges which start from T. The ST is kind of arbitrary. Either the Alice can put on her side of the stream or Bob can put on his side of the stream. It doesn't matter. This is how the stream is constructed. Okay. Now, is the whole picture now clear? Okay. Alice's stream has these edges E1 to Ek, where these are edges from Sx. Okay. And Bob has the edges, okay, I should rather have circled this U minus A. Bob puts this U minus B. In this picture, I have put ST on Bob's side. Doesn't matter whether I put ST on the first side or the second side. Okay, and what is the key observation? That's what I said earlier. The graph that is now broken into this stream. It's the same graph that we constructed, right? It's just that it's put edge by edge onto the stream is connected or not depending on whether A intersection B is 0. This gives a lower bound for graph connectivity. So suppose you had a streaming algorithm to check graph connectivity which used fewer than n bits. Suppose any algorithm, the one designed by the smartest person, if it used fewer than n bits, then Alice has this set A and B. Now he knows that graph theory people are way ahead of us, so I can use some graph streaming algorithms to solve my disjointness problem. So Alice will quickly cook up all these edges based on her knowledge of A and hence A complement, put that in the first part of the stream. Bob will similarly populate his side of the stream, and then they will commission this computer to do the streaming algorithm using this fewer than n storage. The streaming algorithm will start on the first set of edges. You will steal the memory footprint of the algorithm, pass it across the communication channel. Since the supposed algorithm only used fewer than n bits, you needed to send only fewer than n bits across the globe, so you pay fewer than n bits of money. And then Bob will kickstart the same algorithm but with this stolen memory footprint, and once it is done, the connectivity, the answer to the connectivity question which the streaming algorithm gives you is enough to detect whether A and B are disjoint or not. So you ended up solving the disjointness problem by communicating fewer than n bits, which is a contradiction. So there is no algorithm to do this with computing fewer than n bits. Okay, clear? Okay, now yes, okay. In the tutorial session for today, I'll give a start to solve two more lower bounds on checking whether a graph is triangle free or not, and if time permits, we will do perfect matching. And then Venkatesh also left out one question about showing that if a graph has a very large girth, then the number of edges is small. We will try to do these three during the tutorial session. Okay. Before I leave you, I wanted to make this confession that what you saw is just the tip of the iceberg. Okay. There is a lot. I have really diluted this communication game setting in the beginning. Usually the communication game setting is over multi rounds of communication, and also it uses randomized communication. There is also this difference between whether the coin tosses are known to both or known to only one. Okay, so that's the randomized protocol. I wouldn't get into any of that, but this is just a curtain raiser to a big area. Okay, I have followed chapters 18 and 19 from this lecture notes by Amit Chakrabarty, which is freely available online. Video lecture by Saket. There is 2 video lectures in this channel called Math Science channel with this title. It goes into much more detail about the communication games even in the randomized setting. There are also 2 full-sized books on communication complexity, which I have mentioned. Maybe I'll share the slides with you. You don't have to worry about that. Okay. So thank you.